The next step is to prove that this merge algorithm is actually correct. And we're going to do that using loop invariant. Okay, correctness of the merge. To prove the correctness of our algorithm using loop invariant, we have to first identify the loop invariant itself. What condition can we observe in this algorithm that will remain true before the first iteration, after each iteration, and so on? It remains true, and it will help us to actually see that the margin will work. So this is our loop invariant. It says at the start of each iteration of the loop, 1. The subarray A from P until K minus 1 contains the K minus P smallest elements of L and R, but in sorted order. What that means is, if I may just go back to the previous slides, what we are saying in that loop invariant is that before the value of K, so K minus 1, here K is 13, so K minus 1 is going to be 12. Okay, so these elements from P until K, we are saying they are elements from these two subarrays, and they are sorted. You can see 1, 2, 3 is sorted. Okay, yani they are these elements which we have already finished, 2, 1, 2, 3. They are the same elements here, but they are sorted. So if you increment K, we will have copied one more value from either L or R. In this case it is 4. Okay, so again, if you look at this, they are elements from L and R which are sorted. Okay, yeah, these 2, 4, 1, 2, 3, they are the same elements that are now in array A, and they are sorted. This is basically what the loop invariant is saying, that the subarray from P until K minus 1 contains K minus P smallest elements. K minus P smallest elements. If you count them, they are K minus P actually. Let me just show you. Okay, so you see K is 13, P is 9. So what is 13 minus 9? It's obviously 4. 1, 2, 3, 4. So they contain 4 elements from the two arrays L and R, but they are sorted. Okay, the same thing here. If K is 14, then K minus P, 14 minus 9, which will basically give you, again, this time 5, and so on. So that's what we are saying here, that before each iteration, the subarray from P until K minus 1 contains K minus P smallest elements of L and R, but they are in sorted order. I hope this statement is clear. The second part of our loop invariant is that L at I and R at J are the smallest elements of L and R respectively that have not yet been copied back into A. Obviously, we have not copied L at I and R at J yet. Okay, so we're going to see this statement. Is it going to remain true first before the loop starts and also after each iteration? If yes, then we will be able to see that the algorithm will actually work, because that range keeps increasing. And the range I have just shown you of sorted list will keep increasing, and it is sorted, and by the end of the algorithm we will have all the elements in that range and they are sorted. So this means the merger actually will work. Okay, so this is the idea. Now let's do the proof. As we learned, the proving using loop invariant involves 3 steps. You have to prove that the invariant is true before even the loop starts. So this is called initialization. We will show that it is true after each iteration. Before the next one starts, it remains true. And then finally, after the last iteration, it should also remain true. So let's examine the situation before the first iteration. What are these values? So before the first iteration, as you can see here, K varies from P until R. So the question is, what is inside this array? Well, if initially K is P, then this is P minus 1. So obviously the array or the sub-array from P to P minus 1 is empty because the upper limit here is smaller than the lower limit. So this array is empty. Okay, if it is empty, definitely it is already sorted. Alright, so that's what we are saying here. The array is empty and therefore it is trivially sorted. So the first part of the loop invariant definitely is true. What about L I and Rj? Are they the smallest elements of L and R? Well, definitely yes, because I and J are both 1 at this point. Okay, I is equal to J equal to 1. And obviously, since we know that 2 subranges are sorted, definitely L1 and R1 are the smallest elements of L and R. And they have not yet been copied to A. Okay, they are the element not yet copied to A. And therefore, our loop invariant is true initially. Initially, when K is equal to P. So let us see, after 1 iteration, the maintenance. Now, in the maintenance, there are 2 cases. Suppose we enter the loop, we could go to the if part or the else part. We will handle just one of them, the other one is going to be similar. So case 1, if Li is less than Rj, what are we going to do, or what is the algorithm going to do? The algorithm is going to copy Li back to the array A. Alright, and increment I by 1. So now we are saying by the loop invariant, A contains K minus P smallest elements of L and R in sorted order. Also by loop invariant, Li and Rj are the smallest elements of L and R not yet copied. So if we now execute line 13, will the loop invariant remain correct? Alright, the loop invariant was correct just before executing the statements. So now let's see what will happen after executing those. So here we are saying line 13 result in A containing K minus P plus 1. You see the range contains K minus P elements before this assignment. So now we have added only 1. Therefore, the range will contain K minus P plus 1. And since what we have just copied is the smallest element in Li, the subrange in that array A will be sorted as well. Okay, so the line 13 results in A containing K minus P plus 1 smallest elements, but again they will be in sorted order, because all we have done is we have taken one of the smallest elements. I mean the smallest element here, because we see these 2 are the smallest not yet copied, and we have checked which one is the smallest among them. and it is that one that we copied into array A. Therefore, the subrange there that has been copied back to A will remain sorted. Now, incrementing I and K will now re-establish the loop invariant. Okay, because after doing this copy, we only updated I to I plus 1. And of course, K will be updated to K plus 1. So we have only increased I, okay, by 1 and K by 1. So the number of elements remain the same between the array A and the subranges. I hope this is clear. We can follow the same argument for the else part. In case it is the element in R that is smaller, then it is the only one we're going to copy back to the array A, and the loop invariant will remain true as well. Let's look at the termination. What will happen at the end? Well, on termination, what is the value of K? You see, K is going to go from K until R, but actually it will stop at R plus 1, because it is R plus 1 that will make the condition to be false, and we will exit from the loop. Okay, so now the question is, if K is R plus 1, what will be the meaning of K minus P? Let us try to do it. So if K is R plus 1, K minus P will be the same as R plus 1 minus P. And we can simplify this as R minus P plus 1. Okay, so it means by the loop invariant, A contains R minus P plus 1 smallest elements of L and R in sorted order. But what is this R minus P plus 1? This is actually all the elements in A. All the elements, because remember we said to know how many elements are in a range, you will say the last index minus the first plus 1. Well, the last index is R. The first index is P plus 1. Okay, so clearly by the end of the loop, our array A will contain all the elements of L and R, except of course for the infinities. So L and R together contains R minus P plus 3 elements, if you recall. But there are 2 extra sentinels in L and R, so you can see that both the 2 sets A and L and R will actually contain the same set of elements, which means we have now merged all the elements of L and elements of R back into A, and they are in sorted order. So this shows that the merge algorithm actually works. Okay, now that we have shown that the merge algorithm is correct, the next step is to try to analyze it, and then after that we try to analyze the whole merge sort algorithm itself. So this is the algorithm once again. We're going to try and analyze it. However, instead of what we used to do, where we look at each and every line separately and have one row in our analysis table, for that we will try to do it in a more summarized form. And actually this is how you do it if you are really analyzing a big algorithm. You don't have to go line by line. So anyway, let's see how it goes. So to find the running time of merge, we observe that each of lines 1 to 3, line 1, 2, 3, and lines 8 to 10, so 8, 9, 10, takes constant time. and there is no loop involved in these lines. This is just assignment, and creating two arrays. Similarly, line 8 is just assignment. So these are all constant operation. There is no loop that depends on the size of the input in these statements. So we can clearly say the cost of these 6 lines is constant, or we can say is theta of 1. Now the for loops of lines 4 to 7, we have 2 for loops here, for I from 1 to N1 and for J from 1 to N2. Each of them is doing an assignment statement in the body. These 2 for loops will take theta of N1 plus N2 times. This will take theta of N1 times. After that, we have to do this one that will take theta of N2 times. So together, they will take theta of N1 plus N2 times. But N1 plus N2 actually is N, where N is the total number of elements in A. So we can say these 2 loops will take theta of N, where N is R minus P plus 1. Okay, the actual number of elements we are considering in the array A, starting from index P until index R. Alright, so that leaves us with just this for loop to take care of. Now there are n iterations of the for loop from lines 11 to 16, each of which takes a constant time. Yeah, so first, if you look at the body of this for loop, there is no inner loop inside. They are all either comparison or assignment. Either comparison or assignment. Whether we go to the if part or the else part, it just involves some comparison and some assignments. 2 assignments particularly, copying the element Li to AK or Rj to AK, and then incrementing either I or J. So these are constants. So the main thing therefore is to ask how many times are we going to do these constant operations. Well, the loop is running from P until R. Okay, and if you recall, P is the initial index of the first subrange, and R is the last index of the last L range. So actually we are going through the entire array. Not the entire array A, but all the elements from all the n elements basically from P until R. Therefore, its running time is going to be theta of n. So there you have it. We have constant, we have theta of n, and we have theta of n. Therefore, what can you say about the overall running time of this algorithm? Well, it's going to be theta of n, because the highest degree of n is 1, and here we just it's just like saying n plus n, which is 2n. So the running time is still n. We're going to ignore the constant. So therefore, the overall running time of this merge sort is theta of n. Great. So now that we know the running time of the merge algorithm, what can we say about the running time of the merge sort algorithm itself? The merge is only a part of the whole algorithm. So what about the main algorithm? So I repeat the algorithm here just to allow us to do the analysis easily. The running time of the merge sort. Okay, so it's for simplicity and actually without losing generality, we're going to assume that n is a power of 2. So that each divide step will yield 2 subproblems, each of exactly n over 2. Okay, so for example, if you have n to be equal to, let's say, 16, then we're going to keep dividing by 2 So 16 will reduce to 8, 8 will reduce to 4, 4 will reduce to 2, and the 2 sub-arrays, each of size 2, and so on. And 2 will give us 1 element each. Okay, so this is when the division will stop. So if you assume n to be a perfect power of 2, okay, it doesn't matter whether it is not it's power of 2 or not. This is just to make the analysis a little easier. So the base case will occur when n is equal to 1. As you can see here, when we reach 1, definitely p will not be less than r. They will actually be equal. So that will be the base case, and the algorithm will actually just stop. In that case, there's nothing to do. The array is already sorted. But when n is greater or equal to 2, then the if statement is true. And we have a number of things to do there. 1. Compute q as the average of p and r. As you can see here, we are computing the value of q. This is going to be constant time. Just doing the addition, then the division, then the assignment. So these are constant operations. They do not depend on the input size n. Next, we do the conquer aspect. In other words, we're going to recursively solve the two parts of the problem. One from P to Q and the other one from Q plus 1 to R. So the question is, what is the running time of these two parts? So here you have to do something a little clever. You're going to say, okay, assuming the running time of the original problem is T of n. Assuming the running time of the original problem is T of n. Now you have divided your problem into a size n over 2 and a size of n over 2. So the question is, what is the running time of each of these two subproblems? It is obviously going to be T of n over 2. Okay, this will also be T of n over 2. And therefore, these two together, their running time will be 2 or twice Tn over 2. What it costs to run the algorithm if the size is n over 2, twice that will be actually the cost of this 2. Okay, so that's what we are saying here. So recursively solve the two subproblems, each of size n over 2, will actually give us 2Tn over 2. The combined is the margin part, which we have seen is theta of n. We can now therefore say the running time, the complete merge sort algorithm, if we call it Tn, can be expressed as this. First, if n is 1, then there is nothing to do. The algorithm will just do the checking and stop. So it's theta of 1. So if n is 1, Tn will be theta of 1. If the size that we are considering has just one element, the algorithm will stop immediately after doing the first comparison here. So it's theta of 1. But if n is greater than 1, then the running time will be 2t of n over 2. So we are representing the running time recursively now. T of n will be twice T of n over 2. And T of n over 2, one for each of the subproblems, plus the running time of the merge, which is theta of n. So I repeat it here. T of n is theta of 1 if n is 1, 2 T of n over 2 plus theta of n if n is greater than 1. Now, a recursive expression of the running time, Tn, as above, is called recurrence equation. Sometimes it is called recurrence relation, or simply recurrence. Recurrence here because we are expressing running time T in terms of itself. Okay, yeah, so this type of relationship is called recurrence. In the next lecture, we shall learn different methods of solving recurrence relation, because we want to evaluate this to have a single term that say it is theta of n or theta of n squared without having t on the right side. So to be able to do that, this will be the subject of our next lecture, how to solve recurrence relation. But in any case, even now we're going to try and solve this using what is called recursive tree method. So for now, we shall solve the recurrence for the merge sort algorithm by expanding its recurrence tree. Okay, so let's start. To do this, we rewrite the recurrence equation as follows, where the constant c represents the time required to solve a problem of size n equal to 1. So instead of leaving it as theta of 1, we're going to use c, constant c. Okay, theta of 1 of course is constant, so let that constant time be c. So if we do that, then we can represent the relation like this. Okay, so we say if n is 1, Tn will be c. Otherwise, Tn will be 2Tn over 2 plus Cn. Okay, of course, remember, theta of n is some constant time times n. So with this, we can now be able to expand the recurrence tree and see. So for the original problem, we have a cost of Cn, which is the merge, plus 2 subproblems, each of size n over 2, and therefore they will have a running time of Tn over 2. So if you have to put this in a tree, it's going to be like this. Cn, which is the margin part, plus the cost of solving subproblem number 1, which is Tn over 2, plus another Tn over 2 for the cost of solving the other subproblem. So this will give us the overall running time Tn. Each of the size n over 2 problem has a cost Cn over 2 and 2 subproblems. So basically here what we are saying is, if you represent your Tn as 2 Tn over 2 plus Cn. The question is, what will be Tn over 2? If Tn is this, what is Tn over 2? Well, to do that, just substitute n over 2 into this equation, and you'll see what we have. So this is 2 times t. Now n here will be replaced by n over 2. So actually you have n over 4. N over 2 divided by 2 is actually n over 4. Okay, yeah, plus c n over 2. Remember, we are replacing each occurrence of n by n over 2. So this is what this statement is saying, that each of the n over 2 problems, so this one, has a cost of Cn over 2, which is this, plus the cost of solving 2 subproblems of size n over 4. Okay, n over 4. So 2Tn over 4. Therefore, we can replace this Tn over 2, if you like, by saying this is now Cn over 2 and the cost of solving 2 subproblems, each of size Tn over 4. And this is the same thing, Tn over 4. The same thing here, this can now be replaced. Tn over 2 is equal to Cn over 2 and the cost of solving two subproblems, each of size n/4. So this is what we are representing here as this. Now this can be expanded further if you like, because again, going back, if Tn is 2Tn/2 plus Cn, what can you say about Tn/4? Just substitute n/4 here and you will see what you will have. We will have 2Tn/8, because n/4 divided by 2 is actually n/8 plus Cn/4. Okay, yeah, so this is the point. You can continue to expand. The question is, will this expansion continue indefinitely? Definitely not. Eventually we're going to reach 1, because you see we keep dividing n by 2. The example I gave you earlier is if n start as 16, then when we divide it by 2 we're going to have 8. When we divide by 2 we're going to have 4. When we divide by 2 we're going to have 2. And when we divide by 2 again we're going to have 1. When we have 1, the recursion will stop. We will not divide by 2 again. Well, this is just explaining that the Cn are actually the cost of doing the division and the margin, but the Tn/whatever are the cost of solving the subproblems. So you have to combine them together by addition. So this 3 actually is addition. We have to add each node. So this plus each of this plus each of this and so on will give us the overall running time Tn. So this is what you have after some expansion. The interesting point to note is that actually each level of this tree will have the same cost. Okay, so for the original problem, we have Cn, which is the cost of doing the final margin. But this Cn/2 plus Cn/2, if you add them together, you're also going to get Cn. And then this Cn/4 4 times will also actually be Cn. And you can continue to do the division until you reach constant. Well, when n becomes 1, T of 1, of course, is constant. This is what the base case told us, if you recall. T of 1 is equal to a constant. And if there's only one element, so n is equal to 1, the cost of the running time is theta of 1, if you remember, which is constant. So this is why we're saying the bottom level will all have C's, and actually there are going to be n of them. Okay, there are going to be n of them. So again, if you add all these C's, you're going to get Cn. Alright, so we're almost there. All we need to know now is what is the depth of this tree. Because if we can know the depths, to know the overall running time of our algorithm, we just multiply by Cn. Okay, so for example, if the depth is 10, so 10 Cn will be our running time. T will be equal to, running time will be equal to the depth times Cn. Depth times Cn. So if the depth is 10, then our running time will be 10 Cn. And you can see this one doesn't involve T. So we can say, we can clearly find the theta of this one. Just eliminate the constant and we'll be able to get the answer. Right? The question is, how do we find this depth? Now here you should observe something very interesting. These numbers that you are having, initially n, you can consider n as over 1. Okay, they are all powers of 2. All right, so you can think of 1 as 2 to the power 0. This 2, you can consider it as, so this is Cn over 2 to the power 0. Cn over 2 to the power 1, because 2 is 2 to the power 1. And this one will be Cn divided by 2 to the power 2. And this is how it will continue until when you reach constant. So at that time when you reach constant, all it means is this and this are the same. Okay, so you are able to represent sorry, not n, 2 to the power d. We will reach some d which will be equal to n, so that you have 1. Okay, this is when you're gonna reach when you're gonna get this constant c. I hope you get the point I'm saying. We know that t of 1 is c. So the question is, what is the value of d that will be equal to n? I mean, so that 2 to the power d will be equal to n. Because if you have that, then n over n will be 1. And that is when you're going to get this c. If you can know that d, then you will be able to find this depth. You just need to add 1 to it. Okay, because we're counting from 0, 0, 1, 2, 3 until d. Okay, so this is the idea. So we are saying, therefore, in the next slide, to find, we can calculate the depths by determining when the recursion gets down to a smallest problem size. In this case, problem of size 1. Okay, since at each level we are dividing by 2, so at the last level we will have n divided by 2 to the power d to be equal to 1. So the question is, what is this d that will give us 1? Well, we can solve it from this equation very easily, because clearly if n over 2 to the power d is equal to 1, it means n is equal to 2 to the power d, or 2 to the power d is equal to n. So how can we find d from this equation? Take the log to base 2 of both sides. All right, so on this side we have log, I will add to base 2 of 2 to the power d, and log to base 2 of n. Just take log to base 2 of both. Here you can see, if you do that, we can take d before the log. We can say this is the same as d times log to base 2 of 2. Okay, equal to log to base 2 of n. Now log to base 2 of 2 is actually 1. So basically what we are saying is d is in fact log of n to base 2. Okay, because this is 1. Log of a number to the same base is always 1. So this is the idea. Actually d is equal to log of n to base 2. I will show you this is always the case. Let's go back to the original example I was giving you. Suppose n is 16 again. So if you divide, you're gonna get 8. If you divide by 2, you will get 4. Okay, so if you divide again, you get 4. If you divide again, you get 2. And if you divide again, you get 1. Okay? The question is, how many labels do we have? 1, 2, 3, 4, 5. Okay? So our D is actually 4. Remember, D is 4. We will add the 0. This is because this is the 0 level. 0, 1, 2, 3, 4. So our D in this case is 4. If you add the 0 level, then we have total of 5 levels. So the question is D equal to 4 in this case if we follow this algorithm? Well, let's see. What is log to base 2 of 16? Well, this is equal to log to base 2 of 2 to the power 4, which in fact is 4. So the answer is actually correct. D is log to base 2 of n. So with this, we can go back to our Tn, and we will be able to solve it now easily. We'll just say the D plus 1 times the Cn, because each level costs Cn. All right, let's do that. Yeah, so D is log to base 2 of n, and therefore, since we are representing now the depth by log n. Now this is the notation used by our book. Log to base 2, a number, will be represented simply as Lg of n. So if anywhere you see Lg, it means log to base 2. We don't have to say to base 2, we can just use Lg. Alright, so this is our tree now. It is a tree of depth Lg of n, but actually plus 1, as I keep emphasizing, because we start counting from 0. And each level costs Cn. So what is the total? So the total, therefore, since each level costs Cn, each time we go down one level, the number of subproblem doubles, but the cost per subproblem halves. So the cost per level remains the same. There are log n plus 1 levels, okay, where the height of the tree is log n. So with this, therefore, we can say the total cost is the sum of the cost at each level, and therefore, since there are log n plus 1 levels, we just need to multiply the cost of each level. So we're going to have Cn log n plus Cn. And obviously, this is going to be theta of n log n. This is the running time of the merge sort algorithm. Okay. Now, recursive tree expansion like this is not considered to be full mathematical proof. After getting your answer, you still have to do a proof by induction to show that this is indeed true. This is being left for you to do as exercise in the book. It's going to be exercise 2.33. So that's the end of the analysis and also end of the lecture. I'll just give you a few exercises as usual. The first one is straightforward. It says, using figure 2.4 as a model, illustrate the operations of merge sort on the array which has these values. So you just need to follow that figure, keep splitting the array into 2 and 2 and so on until it reduces to single elements, and then do the merging process back up to sort the array. So this is straightforward. Second problem, rewrite the merge procedure so that it doesn't use sentinels. Instead, it will stop once either array L or R has all its elements copied, and then copy the remainder of the other array back to A. Alright, so you have to be checking each time, have we finished at least one of the array? If yes, then all we have to do is copy the remainder in the other array back to A. This is exercise 2.3-2 in the book. Next one, this is the one I referred to in the last slide. Use mathematical induction to show that when n is an exact power of 2, the solution of the recurrence Tn equal to 2 if n is 2, or 2Tn over 2 plus n if n is to the power k, for k equal to, for k greater than 1, is actually n log n. If n is an exact power of 2, then Tn is n log n. So this is what we got using the tree. This question is simply saying, okay, prove it using mathematical induction. Still more exercises. Next one is saying we can express insertion sort as a recursive procedure as follows. In order to sort an array from 1 to n, we recursively sort an array from 1 to n minus 1. So this is how we normally do recursion from data structure. Instead of dividing the input size into 2, we just subtract one element and try to do try to solve the subproblem with of size n minus 1. After that, we try to take care of the remaining element. So this exercise is asking you to do the same. Recursively solve a problem of size a from 1 to n minus 1, and then the element a at n now insert it in this sorted array. Okay, into the sorted array a from 1 to n minus 1. So assuming we can write the problem to be in this way, write a recurrence for the running time of this recursive version of the insert sort. And the last one, referring back to the searching problem of exercise 2.13, observe that if the sequence A is sorted, we can actually check the midpoint of the sequence against our target element V and eliminate half of the sequence from further consideration. The binary search algorithm repeats this procedure, halving the size of the remaining portion of the sequence each time. Write pseudocode, either iterative or recursive, for binary search, and argue that the worst case running time of binary search is log n. So this is the searching problem that we discussed before, but now you are asked to consider it as a binary search. I'm sure we all know binary search. The assumption is the array is sorted. So to find a target, we just check the middle element. Is it bigger than our target or smaller than our target? And then decide which half of the array we need to search. So the question is, this binary search algorithm, what is its running time? Follow the same idea that I have just explained. You can use the recursive tree and show that actually the running time is log n, a theta of log n. So this is the end of this lecture. Thank you very much.